Welcome to today's Engineers Newsletter Live broadcast. I'm Mike Byers with Trane, and I'm your host. Today we'll discuss commercial building pressurization. As always, Trane Engineers Newsletter Live is intended to help you better understand system-level operation, properly apply equipment into systems, and learn about issues and technologies. These broadcasts should give you practical ideas to enhance your business in an educational, non-commercial setting. Thanks for joining us. Today's program will meet these goals as we seek to understand the influences and factors of airside systems upon pressurization in commercial buildings. But before we delve into this broad subject, let's give you a roadmap of where we're heading. First, we'll answer the question, why control building pressure? And we'll discuss what causes the indoor pressure to change. Next, we'll discuss some common system configurations used when controlling building pressure. Then we'll cover some basic application considerations, including sensor location and selection. Finally, we'll move to our question and answer session. You can fax questions to the number that will appear on the screen. Now let's meet our panel of experienced presenters. Art Hallstrom, an ASHRAE Fellow and Trane's Manager of Airside Applications Engineering, returns for this broadcast. Once again, Art has brought some equipment with him to visualize and demonstrate the strategies as they are applied in buildings. It's always a pleasure to hear from another airside expert, Dennis Stanke, a staff engineer in Trane Applications Engineering. Dennis will be discussing background issues and introduce us to various system configurations. John Murphy, a senior applications engineer with Trane since 1993, is author of a number of educational materials and articles on airside issues. John will summarize and comment upon control of each system configuration. Following the presentations will be the interactive session. We encourage you to fax your questions at any time during the broadcast to the number on your screen. You should have a fax-in form in your handout materials. While we usually can't get to all of your questions on the air, we do respond to every one. Be sure to include both your email address and your Trane representative's name, clearly written, please. The focus of today's broadcast is on building pressure control. That is, controlling the static pressure difference between indoors and outdoors. Space-to-space pressure control, which is common in hospital and laboratory applications, is beyond the scope of this broadcast. So why is building pressure control important? And what causes this pressure difference to change? Dennis, help us answer these questions and understand some of the basics of building pressure control.
Okay, I'll try, Mike. Building pressure control is important for two key reasons. First, the right level of building pressure helps make the building comfortable and protects it from damage due to moisture. Second, excessive building pressure, either positive or negative, produces physical forces and unplanned airflows that can cause poor building operation, poor occupant comfort, and can shorten the life of the building. If indoor static pressure is greater than outdoor static pressure, the building is positive. Positive building pressure pushes outward on doors and windows. It also causes exfiltration of indoor air by pushing it out of the building through small holes and cracks in the building envelope. A little bit of outward force on doors and windows doesn't hurt anything, but too much can cause problems. Outward swinging doors, such as typical entrances and exits, may stand open without latching. This can be a security problem. Any inward swinging doors may be difficult to open. In fact, the Americans with Disabilities Act sets a legal limit on door opening force. Too much positive pressure can reduce intake airflow and result in poor ventilation. The intake fan can only overcome so much pressure, and excessively positive space pressure can also reduce supply airflow and may result in loss of space temperature control. Sometimes a little exfiltration caused by positive building pressure is a good thing. For instance, whenever outdoor humidity is high, exfiltration of dry indoor air helps keep the building envelope dry. But in the winter, excessive exfiltration of moist indoor air can lead to condensation on cold surfaces inside the walls. This condensation may lead to microbial growth, corrosion, or structural damage. Brick facades, for example, may crumble when condensed moisture in the mortar is exposed to daily freeze and thaw cycles. If indoor static pressure is less than outdoor static pressure, the building is negative. Negative building pressure pulls inward on doors and windows. It also causes infiltration of outdoor air, drawing it through the envelope into the building. A little bit of inward force on doors and windows is okay, but too much can be trouble. In this case, outward swinging doors may be difficult to open. Any inward swinging doors tend to stand open without latching. As before, this impacts building security. Too much negative building pressure reduces exhaust fan airflow. Poor ventilation can result. A little infiltration may actually be helpful in the winter when outdoor air is dry. It can help keep the building envelope dry. But excessive winter infiltration means cold drafts, cold feet, and general discomfort due to poor temperature control. It can also mean cold spots in the space and the ceiling plenum where moisture can condense and mold can grow. Winter infiltration also increases the heating load. And in summer, infiltration of moist outdoor air leads to condensation on cool surfaces within the building envelope or behind the wallpaper. Hidden condensation increases the potential for mold growth and material damage. And summer infiltration increases space latent load. We've said that excessive pressure, either positive or negative, can be bad, but that moderate building pressure can be good. So should the building be controlled to be slightly positive or slightly negative? Well, that depends on the weather. When it's hot and humid, most designers agree that building pressure should be slightly positive. Exfiltration prevents humid air from leaking into the building envelope. When it's cold and dry, many designers agree that building pressure should be neutral or even slightly negative. Infiltration keeps moist indoor air from leaking out through the building envelope. So how much building pressure is needed to get the benefits of pressure control without the problems? Before we can answer this question, we need to understand what causes building pressure to change. There are usually only three driving forces that impact building pressure: the weather, the wind, and the operation of the HVAC system. Let's start with the weather. Whenever outdoor air is warmer or colder than indoor air, the resulting difference in density causes a pressure difference that varies with building height. This weather-dependent pressure difference is called stack effect. Stack effect is usually insignificant in low-rise buildings and very, very important in tall buildings. But how important is it in your building? To help find the answer, ASHRAE gives an equation to calculate the stack effect pressure difference at any elevation in the building. The important variables for this calculation are outdoor air density, indoor and outdoor air temperatures, the height of the neutral pressure level, and the building elevation of interest. Let's look at an example building to get a feel for the magnitude of stack effect. It's only a 4-story building, 50 feet tall, with a neutral pressure level at 25 feet. Incidentally, the neutral pressure level is the elevation in the building where indoor and outdoor pressures are equal. It's usually at about mid-height when only stack effect is considered. On a cold winter day, 0-degree outdoor air is much denser than 75-degree indoor air. This density difference causes a pressure difference across the building envelope, which separates the indoor and outdoor air columns. Solving the ASHRAE equation at ground level, we find that even our relatively short building has a noticeable pressure difference of negative 0.06 inches of water. At the top floor, the differential pressure is 0.06 inches positive. Outdoor air tends to infiltrate at the lower floors. Indoor air tends to rise within the building, then exfiltrate at the upper floors. That's winter operation. In summer, however, the situation is reversed. 95-degree outdoor air is not as dense as 75-degree indoor air. This density difference causes a positive 0.01 inch pressure difference at the ground floor and a negative 0.01 inch at the top floor. Not very significant for this 4-story building, but still, hot outdoor air tends to infiltrate at the upper floors. Indoor air tends to sink within the building and exfiltrate at the lower floors. Buildings experience stack effect when it's cold and reverse stack effect when it's hot. Even in relatively short buildings, significant changes in building pressure can result from air density changes caused by the weather. Everybody talks about it, but nobody does anything about it, right? Well, you can't change the weather, but if you're the architect, you can minimize its effect by compartmentalizing the building. Good floor-to-floor seals reduce the indoor air column height, which reduces stack effect pressure across the building envelope. The engineer's newsletter that accompanies this broadcast includes more detail on compartmentalizing. Now let's consider the second driver. The wind exerts velocity pressure on the windward side of the building while depressurizing the leeward side. Wind may have little impact on a low-rise building or a mid-height building in the middle of the city, but it may be very important for a tall building or a poorly sheltered building in the middle of a field. ASHRAE gives an equation to calculate the wind pressure at any building elevation. The important variables for this calculation include outdoor air density, the shelter factor, the effective local wind velocity, and the wind surface pressure coefficient. Let's consider our example four-story building on a winter day. Remember, the effective wind depends on air density, so cold days are more important than warm days. The building is well sheltered with a 0.4 shelter factor. The effective wind speed is 25 miles per hour. The wind surface pressure coefficient depends on building elevation and wind direction. For our building, we assume it's 0.5 at ground level and 0.8 at the top floor. Using the equation, we find that the wind results in a positive outdoor pressure on the windward side of 0.03 inches at ground level and 0.4 inches at the top level. On the leeward side, it results in negative 0.03 inches at ground level and negative 0.04 inches at the top floor. In effect, the wind changes the effective outdoor static pressure. It tends to push outdoor air into the windward side of the building and pull indoor air out of the building on the leeward side. Stack effect and wind combine to cause building pressures that vary depending on location within the building. On a winter day, the positive 0.1 differential pressure on the leeward side of the top floor of our example building might cause too much exfiltration, and the negative 0.09 inches on the windward side of the ground floor might interfere with door operation. On a summer day, on the windward side, the negative 0.05 inches at the top floor and negative 0.01 inch at the ground floor might cause too much infiltration. If you do nothing to control it, building pressure is likely to be excessive at some operating condition somewhere in the building. To avoid excessive building pressure requires careful planning and a control system that can respond to changing conditions. Here's where the third driving force comes in. It's the mechanical system. In addition to adjusting intake and exhaust airflow for proper ventilation, the HVAC fans and dampers can also be used to control building pressure as operating conditions change. Of course, the difference between intake and exhaust airflow determines net building pressure. Excess intake airflow results in net positive building pressure, which causes exfiltration. Excess exhaust airflow results in negative pressure, which causes infiltration. Intake and exhaust airflow depend upon the HVAC system operating mode. 4 operating modes are important when considering building pressure control. When it's hot outdoors, the system is in the cooling mode. Intake airflow is maintained at the minimum quantity required for proper ventilation. When the weather is mild, an airside economizer may be enabled to reduce mechanical cooling energy. As long as the outdoor temperature is higher than the desired supply air temperature, the system brings in 100% outdoor air and provides the balance of cooling mechanically. We call this integrated economizer mode. Without sufficient relief, building pressure tends to be excessively positive in this mode. When the outdoor air drops below the desired supply air temperature, the system modulates the outdoor and return air dampers to provide free cooling. Mechanical cooling is off because outdoor air handles the entire cooling load. Intake airflow varies between 100% of supply airflow down to the minimum ventilation requirement. We call this modulated economizer mode. Building pressure can vary over a wide range in this mode. Finally, when it's cold outdoors, the system is in the heating mode. The outdoor air damper again maintains intake airflow at the minimum quantity required for ventilation. Many buildings tend to be negative in the heating mode. To control building pressure, most designers place the indoor pressure sensor on the ground floor and set it to maintain the pressure between 0.05 and 0.1 inches positive at all times. This may be enough pressure to prevent infiltration and provide adequate pressure control, especially for smaller buildings in warm climates. But in multi-story buildings, the best set point range really depends on the impact of stack effect and wind on the pressure difference at the top floor. In our example building, summer infiltration at the top floor can be eliminated by raising building pressure by 0.05 inches. This takes a ground floor pressure setting of at least 0.06 inches positive. And controlling to the same pressure year-round may not be the best solution for all buildings in all climates. Sometimes it might be better to change the set point range as operating mode changes. For example, when it's cold and dry outdoors, a neutral or slightly negative building pressure may be desirable to prevent exfiltration of moist indoor air. For tall buildings in cold climates, wintertime stack effect can cause significant positive pressures at the upper floor. In our example 4-story building, top floor exfiltration can be eliminated by lowering overall building pressure by 0.1 inches. This takes a ground floor pressure of at least negative 0.16 inches.
Okay, it was important to get everyone on the same sheet there with regards to building pressurization influences. Let's take a moment to summarize. First, if building pressure is not controlled, the physical force of the indoor to outdoor pressure difference can interfere with door operation. Second, unplanned airflow that results from this pressure difference can lead to discomfort, or worse, condensation and damage to the building itself. Both excessively positive or excessively negative pressure can lead to problems. And the driving forces for changing pressure in the building include the weather, wind, and the mechanical system. And while we can't control the weather or wind, prevailing conditions should be taken into account by the designer. These driving forces may or may not be critical in your building, but even a one-story building experiences stack effect. It's just not real important because the pressure differences are so very small. Finally, when it's hot and humid outdoors, the building should be slightly positive. When it's cold and dry, the building should be neutral, or maybe even slightly negative in some climates. In this next section, we'll discuss some of the most common system configurations that are used for controlling building pressure. Let's review a few definitions to make sure that we're all on the same page. This slide defines the airflows, fans, and dampers most commonly used for controlling building pressure. Now, we probably need to clarify the difference between exhaust air and relief air. The air that leaves the building for the purpose of removing contaminants we call exhaust air. Local codes or industry standards define the amount of exhaust air that must be removed from certain types of spaces, such as restrooms. This air may be exhausted locally at the source or from a central location. The air that leaves the building for the purpose of balancing the intake airflow and maintaining proper building pressure we refer to as relief air. Similarly, this air may be relieved locally or from a central location. Okay, Dennis, go ahead and introduce our first configuration.
Okay, Mike. Our first system configuration for controlling building pressure actually uses no control at all. Outdoor air enters the system at the air handler. Some of this air is exhausted by local fans. The remainder leaves the building by exfiltration. Every building has the capability to naturally relieve some amount of air through holes and cracks in the building envelope, as well as through doors and around windows. Natural relief may prevent excessively high positive pressure in low-rise buildings with simple, constant volume HVAC systems, but it may not work as well if the system includes an airside economizer. Even without an economizer, the building is likely to experience wide fluctuations in building pressure as outdoor conditions change. We built a model of a small building and air handler. Here's Art and John to demonstrate natural relief using the model.
Thanks, Dennis. Here's a model of a building with an air handler, and we constructed it simply to show you firsthand what building pressurization really can do to a building. And we're going to start with a demonstration of natural relief. Now, this is a relatively small building. It's roughly about 2 feet by 2 feet by 3 feet long. On top of the building is an air handler, and we have two parts of the air handler. There's a supply fan section containing a centrifugal fan, and typically this would be where your coil and your filters would go. We left that little impeller that came on the front of the fan strictly so you can see that the fan is operating and how fast it's operating. The other section of the unit's replaceable. Right now we have a mixing box section to demonstrate a rather simple air handler. Later we can change this and make it a return fan or a central relief fan. In the building itself, we have a couple things to show you in terms of external appurtenances. One is a door. The door is simply a door for the building. It would be hinged on one side typically, and it can be locked or unlocked as the case might be. Here we have barometric damper on the side of the building, and this again lets the pressure out from inside the building. Now this is a real barometric damper that we're able to obtain, a Bentley, a very small one. But it's center hinged, and as pressure would build up in the space, it will be relieved simply through the barometric damper that's located in the wall of the building. The supply fan itself can deliver about 100 CFM, constant volume. The volume of the building is rather small relative to the amount of air that fan can deliver, so that the changes that occur in the building relative to static pressure will occur a lot faster than what you'll see in a real building. But we did that for the speed related to this broadcast. Sealing the building was a real issue. The plenum area, particularly around the top, becomes a concern because it's a leak rate for exfiltration or infiltration. Just got to watch that in your building. On the mixing box, we had some very small low leak dampers built. These are very miniature versions of what you might see in a real rooftop or an air handler. Basically a single parallel blade damper, low leak seals around the damper. And John's demonstrating how they operate. To measure the static pressure in the building itself, we have a Dwyer photohelic gauge. It's measuring the internal static pressure through a tube inside the building relative to the outside static pressure, which is measured by our outdoor static pressure gauge. It's a zero-centered gauge. The black needle represents the static pressure in the space relative to outside. The red needle on the right is set for plus 0.5 inches static, or 125 pascals. The one on the left would be a negative 0.5 inches static. John, let's go ahead and turn on the supply fan, and we'll see a demonstration of natural relief. Right now, the outside air damper is closed. The return air damper is fully open. Basically, the air is simply recirculating within the model. You can see the static pressure really doesn't change. Now, if we increase the amount of outside air going into the space, in other words, the ventilation air, you notice the static pressure start to rise in the building, 1/10 of an inch. But if you go to full economizer, the static pressure really jumps in the building, in this case as high as 0.5 inches positive. John, how do these pressure changes occur through the 4 system operating modes?
Well, during the cooling mode, the system brings in the minimum quantity of outdoor air required for ventilation. If the building envelope is leaky enough, natural relief may be able to prevent building pressure from becoming overly positive in this mode. In the integrated economizer mode, however, the system brings in 100% outdoor air for free cooling, and building pressure rises. How high it rises depends on how tightly the building is constructed. In the modulated economizer mode, intake airflow varies, so building pressure varies between this high value and the normal level. During the heating mode, the system again brings in the minimum quantity of outdoor air. Depending on how cold it gets outdoors, natural relief may result in positive or negative pressure during this mode.
John talked about overpressure issues in a building with natural relief, and we can demonstrate that with our model. In a real building, doors would typically be in use, and we can demonstrate what happens when the doors are activated. John, throttle the outside air back to 0, and I'm going to unlatch the door on the front of the building. Now, when the outside air is increased to the space, boom, you'll see the little door literally pop open. In fact, this door is very hard to close. If I go up to it and push the door closed, I'd have to push it closed hard enough to let it latch against the lock. This could even create a potential security problem for the building because the doors are essentially open to the space. It also could cause airflow problems in the building, which result in poor temperature control.
Natural relief may be suitable for small, less tightly constructed buildings that have constant local exhaust operation and no airside economizer. However, the building may still experience fairly wide fluctuations in pressure due to other influences. Finally, buildings constructed with tighter envelopes may not offer adequate natural relief and be overly positive much of the time. Dennis, let's get into some system configurations that are better able to control building pressure in response to these changing conditions.
The mechanical system can be used to control building pressure by varying either intake airflow or relief airflow. Most designers choose to vary relief airflow because minimum intake airflow must be maintained for proper ventilation. That's what we focus on in this broadcast. Intake airflow modulation is sometimes used when exhaust airflow must be very high, like in hospitals, but these systems are outside the scope of today's broadcast. We've already looked at natural relief. Next, we'll consider local relief through a damper in the occupied space. For local relief, a non-motorized, gravity-operated relief damper, commonly called a barometric relief damper, is installed in or near the occupied space. Outdoor air is brought in by the air handler. A mixture of outdoor air and recirculated return air is supplied to the space. In some of the space, supply air is exhausted by local exhaust fans. The remainder either returns, exfiltrates, or finds its way to the local barometric relief damper connecting the space to outdoors. As the positive pressure in the space increases, the relief damper is forced open, allowing air to leave the building and preventing the building pressure from becoming too positive. Now let's watch Art and John again as they play with the building models.
Thanks, Dennis. Local barometric relief dampers can be demonstrated with our model. Now, barometric dampers allow positive air pressure to leave the building through an alternate route than the front door of the building. Here's a real but very small barometric damper. Notice the shape. It's hinged at this point in the middle, so it's counterbalanced. The extra metal on the top offsets much of the weight below. So when the damper is fully deployed, it requires about 2/10 of an inch static pressure to open the damper fully up. Now, we placed one of these local barometric dampers in the building wall. We can show you how it works. Let's turn on the supply fan. We'll go from 100, basically right now we're at 0% outside air. Let's go to 100% outside air. Watch the pressure gauge and the barometric damper. Fully deployed, the barometric damper is open. Building pressure increases by just 2/10 of an inch, not 5/10 as in the last example. John, could you please discuss the 4 building operating modes?
Sure. During the normal cooling and heating modes, local barometric relief behaves just like natural relief. However, in the economizer modes, when the system brings in more outdoor air, this relief damper is forced open to prevent building pressure from rising too high. In many buildings, local barometric relief may be suitable for preventing overly positive pressure during these economizer modes. Also, the relief dampers are relatively inexpensive to install and require no additional controls or pressure sensors. However, multiple dampers are often required to minimize the effects of wind, and the dampers must be properly sized. They need to be large enough to relieve enough air to prevent overly positive building pressure. The relief dampers are typically located in the conditioned space or possibly in the open plenum near the space. This does create another opening in the building envelope, increasing the risk of unwanted air leakage. Therefore, they are most commonly used in smaller buildings with ceiling plenum returns.
Barometric damper location is very important in the building. You can see in our example here that if you place in the side of the building where the wind was going to be impacting and maybe the prevailing winds are coming from this direction and they hit the barometric damper, they're going to have a tendency to close it. If they start to blow it closed, you're going to start seeing the static pressure in the building going up. Consider locating barometric dampers on the various faces of the building. Barometric seals are very important. Remember, you have a hole in the building. You want to prevent infiltration back into the building when the damper is closed. Consider insulating the barometric damper. And then finally, you'll probably want to put a bird screen behind it to make sure that no birds end up in the building. Local barometric damper sizing is important. Typically, they're sized for full CFM exhaust at 0.2 of an inch static pressure. Dennis, what's next?
To reduce the cost associated with installing multiple local dampers, some designers have attempted to use a single barometric relief damper located in a roof-mounted air handler or packaged rooftop air conditioner. We call this system configuration central relief damper. Some designers specify a central relief damper installed in the mixed air plenum downstream of the return air damper. Others would like it located in the return air plenum upstream of the return air damper. Do either of these central configurations really work? Let's go back to Art and John to see if they can show us the answer.
Okay, Dennis, a demonstration of central barometric relief. We're going to take the barometric damper that was located in the sidewall of the building and we're going to move it over to the unit, calling it a unit-mounted central relief. Now that damper can be placed either upstream of the return air damper or downstream of the return air damper. For the purpose of this demonstration, we're going to put it downstream of the return air damper and show you the result. John, would you unlock the damper? Okay, then we're going to turn on the supply fan to full air. And John's going to increase the outside air to the space. Now, as he does, the supply fan will take the outside air, put it into the space. We're noticing the building static pressure start to go up. But yet our barometric damper simply does not open. Why? Because it's located after the return air damper. It's in a suction side of the air handler. In fact, that damper will never open up. You don't need to bother with it. It's a poor location. Using unit-mounted barometric relief dampers, put them upstream of the return air damper.
Locating the relief damper in that position before the air reaches the return air damper allows the return air plenum to be at a positive pressure while the mixed air plenum can be negative. During the cooling and heating modes, this configuration behaves just like natural relief. In the economizer modes, however, building pressure must increase enough to overcome the pressure drop of the return air path before this central relief damper is forced open. The combined pressure drop through the return grill, ceiling plenum, any return ductwork, and the return air plenum of the air handler may be 0.3 up to 1 inch or more. The space must be overpressurized by this amount before this central barometric damper even cracks open. Centralized barometric relief requires fewer dampers, needs no controls or sensors, and can be easily packaged in roof-mounted equipment. But remember to locate this central damper in the return air plenum before the air reaches the return air damper. In this configuration, it works better than natural relief, but this approach relieves air only under very positive pressure conditions. Often, the air instead finds less restrictive ways to leave the building, like through the doors. Dennis?
We move on now to two control methods used with the central relief fan configuration. In the first method, the relief fan controls building pressure indirectly without actually sensing it. Sometimes called central exhaust or powered exhaust, this system simply turns on the relief fan whenever the outdoor air damper opens to a predetermined position, such as 30% of full open. The two-position motorized relief damper opens when the relief fan is on and closes when the relief fan is off. Neither fan capacity nor damper position is modulated. During cooling and heating modes, when the system is bringing in the minimum quantity of outdoor air, the relief fan is usually shut off, and any building pressure relief occurs naturally. Art, can you and John show us this one?
Using the building pressurization model again, we've replaced the mixing box with a module that includes a central on-off relief fan. That's this section of the model right here. Briefly, it has an outside air damper, a return air damper, a central relief fan, and a central relief damper. And we'll be using these two in an on-off configuration to help control building pressure. Notice the central relief fan is in parallel with the supply fan in terms of a unit configuration. Let's go ahead and turn the supply fan on with the air set at minimum outside air to the space, or in other words, a slight building pressurization. If the unit goes into the economizer mode, we'll bring on 100% outside air to the space. That increases the space pressure. To control that, we would then turn on the central relief fan and at the same time open the relief damper to its full position, thus bringing the space back close to neutral static pressure. As the outside air damper modulates closed in the modulating economizer mode, you'll see a slight decrease in space pressure. As the outside air continues to be reduced, space pressure will go further negative until we simply turn the central relief fan off. John?
Let's look at the 4 system operating modes again. During the cooling mode, the relief fan is off and the building naturally relieves. In the integrated economizer mode, the system brings in 100% outdoor air for free cooling. The relief fan turns on to prevent the building pressure from becoming overly positive. In the modulated economizer mode, intake airflow varies between 100% of supply and the minimum required for ventilation. As the outdoor damper begins to close, less air is brought into the building and building pressure begins to decrease, eventually becoming negative due to constant relief airflow. When the outdoor damper reaches a predetermined minimum position, the relief fan is turned off and building pressure again becomes positive. Finally, during the heating mode, the outdoor damper is at its minimum position, and depending on how cold it gets outdoors, the building pressure may be positive or negative. Now, this on-off control strategy prevents overpressurizing the building during the economizer modes. The relief fan and controls can be easily packaged in an air handler, and no additional pressure sensors are required. Control is very simple. The relief fan is turned on and off based on the position of the outdoor damper. This allows a relief fan to be turned off for many hours of the year, saving energy. However, the building will experience some fluctuations in pressure and may become negative during the modulated economizer mode. So proper air balancing is critical to ensure that the building does not become too positive or too negative. Next, Dennis is going to introduce another way to control this central relief fan.
The second control method modulates the capacity of the central relief fan to control building pressure directly. This is sometimes called direct pressurization control. A sensor measures the difference between indoor and outdoor pressures. If it's below a low pressure limit, the relief fan is off. If it's above a high limit, the controller modulates the relief fan capacity to keep the building pressure within the desired range. Fan capacity modulation may be accomplished with inlet vanes, a variable speed drive, or by varying the position of the relief damper and simply riding the fan curve. Directly measuring building pressure allows the system to respond to changes caused by stack effect, local exhaust fan operation, and airside economizer. Now, we've been talking about constant volume systems. VAV systems have an additional challenge. Because the supply airflow varies, the required percentage of outdoor air changes. One way to assure proper ventilation is to measure and maintain outdoor airflow. This can be accomplished using an airflow monitoring station and a modulating damper, or a combination flow measuring damper. In this example, we show a flow measuring damper modulates to maintain the proper intake airflow as supply airflow varies. As in the constant volume example, the controller modulates the capacity of the relief fan to keep building pressure in the desired range. Now over to Art and John again to demonstrate this configuration. Things are getting more complicated, eh guys?
Complicated, but not complex. Actually, we're going to talk about now modulating the central relief fan to control space pressure. Modulating the exhaust will allow you to control space overpressures. And I'm going to do that with basically a fan speed switch we've hooked up to the central exhaust fan. Now, John, for this demonstration, I'll need your help. Let's turn on the outside supply fan. Outside air damper is at minimum outside air. And I'm going to turn on the relief fan so it's operating at the slowest possible speed. Now, as the static pressure starts to build in the space, John's going to increase the outside air. It'll build up the pressure in the space. As the space pressure goes up, I'm going to increase the exhaust rate from the central relief fan, trying to keep the space within a 0 to 0.1 of an inch positive. 100% outside air.
Yep.
Now John can modulate the outside air back slowly. As he does, I will reduce the exhaust rate, pretty much keeping it within the control band that we would like to have for the building. John.
This direct method of controlling the relief fan allows the system to dynamically respond to changes in building pressure. During the cooling and economizer modes, building pressure can be controlled directly so it is slightly positive with respect to outdoors. During the heating mode, the set point is changed in this example, and building pressure is controlled to be neutral. Modulating the central relief fan can provide very stable control of building pressure. It allows the HVAC system to respond to changes due to wind, stack effect, local exhaust fan operation, and airside economizing. And you can change the set point range during these different operating modes. The central relief fan can be positioned anywhere in the return air path, which provides greater flexibility and possibly a lower installed cost than a system with a central return fan. However, central relief fans may not be suitable for some systems with high return path pressure drops. If the supply fan cannot overcome the combined pressure drop of the supply and return air paths, a return fan may be required. Also, proper location and selection of the indoor and outdoor pressure sensors is critical to providing stable control. Now, Art's going to discuss sensor location and selection later in the broadcast, but next, Dennis is going to discuss return fans.
Okay, we've talked about 4 configurations so far. We're almost done. The final configuration uses a central return fan instead of a relief fan. Like the relief fan, several control methods can be used. During this broadcast, we'll discuss 5 control methods. The first is sometimes used in constant volume systems. It simply turns on the return fan whenever the supply fan is on. Both supply and return airflow are constant. Building pressure is not sensed. The outdoor, return, and relief dampers are usually linked and controlled by a single actuator. The system can be balanced to maintain a slightly positive building pressure in cooling mode. However, without direct control, building pressure may fluctuate widely in economizer and heating modes. Art, can you and John demonstrate this one?
Sure. We've replaced the relief fan module with the return fan module. The return fan is now in series with the supply fan. We have a relief damper, an outdoor air damper, and a return air damper. The return fan air volume can be offset from the supply fan air volume to allow for remote exhaust and exfiltration. In a typical unit, the outside, return, and relief dampers would all be linked together. In this case, we fixed the outside, return, and relief dampers for the desired building pressure. John, If we open the outdoor air damper and close the return damper and the relief damper all together, we can maintain the building static pressure. This rather simple system is fairly effective on constant volume systems for maintaining space pressure.
Yeah, this simple strategy may be adequate for constant volume systems with constant local exhaust. No pressure sensors are required, and the controls are pretty simple. In some cases, the supply fan motor can be smaller than in a system with a central relief fan. This is because the return fan offsets the pressure drop of the return air path. However, the building may still experience some fluctuations in pressure during economizer modes. Realize now that equal rotation of these dampers does not necessarily mean equal changes in airflow. Proper selection and sizing of these dampers is very important, and air balancing is critical for ensuring that the building pressure does not become too positive or too negative. Finally, layout options are somewhat limited. The return fan draws air from the space through the return air path and pushes it through the return air damper. This requires the return fan to be located between the nearest space and the return air damper. Back to you, Dennis.
Now let's talk specifically about VAV systems. Controlling the return fan is not quite the same as in the constant volume system. You can't balance your way to success because the supply airflow and the required return airflow change continually. The second control method uses airflow tracking to indirectly maintain building pressure. An airflow sensing station determines supply airflow. A controller subtracts a fixed value to compensate for local exhaust and exfiltration to find the return airflow set point. The controller senses return airflow and modulates return fan speed to maintain the calculated set point. Building pressure is indirectly controlled provided the airflows are sensed accurately. A third control method involves both fans receiving the same capacity signal based on supply duct static pressure. This approach doesn't control building pressure very well in VAV systems because the return fan curve is not identical to the supply fan curve. If used, it's likely to result in wide fluctuations in differential airflow and building pressure. A fourth control method adds hardware to adjust return fan capacity in order to directly control building pressure. A controller modulates the relief damper to maintain the building pressure in the desired range. The return fan is then modulated to maintain a constant static pressure in the return air plenum, downstream of the fan. This method can maintain building pressure in the proper range in all operating modes. However, locating that static pressure sensor in the return air plenum can be a challenge due to turbulence downstream of the fan. So Art, do you guys want to try to demonstrate this system, or is John just going to talk about it?
No, we're going to try and demonstrate this one. This is a return fan unit again. Let me walk through briefly the 4 control loops for you. Being a VAV system, the VAV supply fan is controlled by the duct static pressure. The outside air and the return air dampers are controlled by a mixed air thermostat in the mixed air chamber. The relief damper is used in controlling space static pressure. And the final one is the return fan CFM, which is being controlled by the pressure in the return air plenum. Interactively, they all work together. You can see there's 4 individual control loops. Now, whenever you make a change to one of the 4 control loops in terms of flow, CFM, or static, you change the other 4. And the trick with this system is to make sure they all remain stable. John, could you start us out by changing us from a minimum outside air to full economizer outside air and describe the steps you do?
Sure, Art. Just to know where we're starting from, at minimum outdoor air, we had the building pressure within our set point range that we want, between 0 and 0.1 inches. We're also controlling the return fan capacity to maintain about 1/10 of an inch in this return air plenum. So if we go to economizer mode, open up the outdoor air damper, close the return air damper, what happens is our building pressure is going to go up a little bit, so we're going to open our relief damper to get building pressure back down, we also increase the return air plenum pressure quite a bit. So we're going to slow the speed of the return fan down as we get back down to its set point. What we see over on the building pressure gauge is it went back up again. So we need to relieve a little bit more air, open up our relief damper a little bit more, which causes our pressure in the return air plenum to go down again, and speed up the return fan. So eventually you can get to a balance point where you're within your set point range on building pressure and you're maintaining your set point in your return air plenum. Just takes a little bit of work.
Right. Control loop stability and timing are critical. Also, one more key point from an applications point of view. The pressure across the return air damper is relatively high, so it's very sensitive to positional changes. Be aware of that when you're setting up your control system. John?
Yeah, this control method can provide stable control of building pressure in a return fan system. In fact, this method of modulating the relief damper to maintain building pressure and modulating the return fan to maintain the return air plenum pressure is recommended by ASHRAE guideline 16P. In some cases, the supply fan can be smaller than in a system with a central relief fan. However, layout options are somewhat limited, as the return fan must be located between the nearest space and the air handler. Also, controlling the fan based on return air plenum pressure requires a pressure sensor in that plenum and a method for modulating the capacity of the return fan. Again, proper location and selection of the indoor and outdoor pressure sensors is critical. Plus, since this return air plenum is generally pretty small and turbulent, it may be difficult to properly locate that sensor as well. Next, Dennis is going to share an approach that may be able to eliminate that particular concern.
One approach that may avoid the return air plenum pressure sensing problem is what we call optimized damper control. It can improve control stability and reduce fan horsepower a little bit in the process. As before, a flow measuring outdoor air damper modulates to maintain proper intake airflow, and a separate actuator modulates the relief air damper to maintain building pressure. In this case, however, a third actuator modulates the return air damper to keep the outdoor air damper nearly wide open. This minimizes the mixed air plenum pressure and supply fan horsepower. Note that none of the dampers are linked. Each has a separate actuator. This is a key requirement for optimized damper control, which we discussed in more detail in our March 2000 broadcast. Using this approach, we may not even need to sense static pressure in the turbulent return air plenum. Instead, we sense relief air and return air damper position. The return fan speed is then modulated to keep one of these two dampers nearly wide open. This minimizes the pressure needed for both relief and recirculated airflow, which reduces return fan horsepower somewhat and can eliminate this sensor altogether. With proper field engineering and balancing, this approach can help to solve one return fan control problem.
Dennis, I know there's always some debate over whether to use a relief fan or return fan. Can you offer us some guidance here?
Yeah, as we discussed in the accompanying engineer's newsletter, building pressure can be controlled using either configuration, but a central relief fan is usually preferred over a central return fan. Here's why. The relief fan can be located anywhere in the return path, but a return fan must be between the air handler and the nearest space. This layout flexibility can reduce building first cost. Only one control loop is needed to modulate the relief air damper, but a return fan needs one additional control loop for fan speed. Fewer control loops means easier tuning and more reliable control system. Also, fewer control devices means lower first cost. The relief damper is usually off during cooling and heating mode, but a return fan must run whenever the supply fan is on. Fewer hours of operation means longer life and usually lower operating cost. One possible drawback, when the relief fan is off, the negative return air plenum may draw in outdoor air through the relief damper. This can be minimized by using low leak relief dampers. Another drawback, The supply fan must have enough horsepower or pressure capability for the pressure drop in both the supply and return air paths. In some systems with high return path pressure drops, a return fan must be used.
Well, we've covered a lot of ground, so let's recap. Barometric relief works well in smaller buildings, right?
Yes. Locating the relief dampers in or near the occupied spaces results in better performance than natural relief. If you use central barometric relief damper, make sure it's located before the return air damper.
What about a central relief fan?
On-off control of a central relief fan may provide adequate building pressure control in constant volume systems with airside economizers. However, in VAV systems, direct sensing of building pressure and modulating the central relief fan offers much better control.
Okay, but how about central return fan systems?
If a return fan must be used because of high return path pressure drop, modulate the relief damper based on actual building pressure and modulate the return fan to maintain return air plenum pressure. And optimized damper control may improve system control.
Okay, one more. Please reiterate the differences between a relief fan and a return fan system.
Well, Mike, I just did. But in a nutshell, the relief fan, our central relief fan, is preferred because it usually costs less to install and operate and is easier to control. But if you must use a return fan, that system can be made to work too.
Okay, well, now that we've considered several system configurations used to control building pressure, we need to discuss some issues. One that comes to mind readily is the question of where do I locate the indoor and outdoor pressure sensors? Art, can you give us some guidance on this?
When positively controlling building pressure with an exhaust, return, or relief fan, you need to measure the differential pressure between indoors and outdoors. Proper selection and location of the two sensors is very important. The indoor pressure sensor can be a simple static pickup probe. The indoor pressure sensing probe needs to be located so it does not pick up wind effects near the doors. A large open space or a central hallway is a good location. It is typically located on the ground floor or any floor with external doors because the effects of over and under pressurization are most noticeable there. Use common sense in locating the sensor. Building pressure equalizes rather quickly in a structure, and it's only stopped by walls, doors, and floors. In a large mall served with 4 air handlers, one indoor sensor can be used for controlling all 4 air handler building pressurization control systems. If individual buildings are connected with enclosed walkways without doors, they're going to act as one big zone. So take steps to ensure that the outside air going into one building does not go out through another building. Failure to do so may create wind tunnels in the walkways between the buildings. Now, accurately sensing the outdoor static pressure is critical to the building pressurization system. It needs to measure an average outdoor static and reject all of the wind gusts. Now, here's an outdoor air static sensing probe that we've had excellent experience with. It's the Dwyer A306. The outdoor pressure signal is picked up here, sent through this expansion tube, and out through the sensing tube. Watch the meter and see how effectively it rejects the wind gusts. A critical design issue is making sure that water does not get into the tube and block the tube. This expansion tank inside the unit makes sure that the water has to go up vertically, and since it doesn't, it keeps it out of this tube. If this tube gets blocked, the system will become rather unresponsive because air cannot get through it. The sensor enclosure is plastic, so it does not rust, and it's red, so it's easy to find on the roof. Just attach it to the building or the HVAC equipment, but put it in a location where people will not tamper with it. The outside and indoor tubes need to be connected to a pressure transmitter that will convert the pressure differential into electrical signals for the building pressurization control system. There are 2 basic types, deadband and digital. This is a typical deadband transmitter for step-based building pressurization control systems. It's a Dwyer photohelic, and it has an adjustable deadband, one for the high side and one for the low side. Simply set the high side over here for what maximum static pressure you want to see in the space, and then set the low side for the negative pressure in the space. When the black needle crosses the high or low limit, it will trip a photocell in the meter which will close a relay. And these relays can be used to increase or decrease the building pressure. The other option is this microelectronic transmitter that's used in a BASD type control system. It converts the pressure differential between the indoor and outdoor static pressure signals into an electrical signal which is read by a controller. The controller is then responsible for maintaining the building pressure at the specified set point. The key is to maintain stability. Building pressurization changes generally need to occur very slowly so that other system components can adjust.
Okay. Dennis, are there any other influences that designers should consider?
Well, while the combined effect of weather, wind, and mechanical system operation determines building pressure, other building characteristics determine the impact of these pressure drivers. First, quality of construction. A poorly constructed, leaky building, it's very difficult to maintain pressure at the desired level. On the other hand, in a well-constructed, tight building, pressure control becomes very important to avoid excessively positive or negative pressure. A well-sealed building saves energy, but makes pressure control a necessity. This is one reason that we think this building pressure broadcast is important. Second, windows and doors.
Many windows means many cracks to seal, and operable windows left open act like large holes
in the envelope.
Improper window installation can cause building. Doors that connect directly outside become
a hole in the envelope when they're open, and they pump air as they open and close. The more often the door is open, the more difficult pressure control becomes. Buildings with high door opening frequency, like retail stores, often act leaky regardless of construction. To maintain building pressure and to assure proper operation, it may be better if doors don't connect directly to outside. That's what vestibules, entrance tunnels, and revolving doors are for. Finally, compartmentalization. Stack effect pressure can be greatly reduced by breaking the building up vertically into shorter pressure compartments. Floor-to-floor air seals and floor-by-floor air handlers can be keys to good compartmentalization. Do you think we covered everything, Mike?
Well, I think so, except for just the questions we've generated, and that's next. We'll now move into our interactive segment,